The Markov decision process. In this section, you will learn about the Markov decision process, dynamic programming, Bellman equations, value and policy iterations in Python, and the value and policy iteration in the Bellman equation in R. Markov decision process. In this video, we will learn about the Markov decision process, dynamic programming, value function, and the Bellman equation. Markov decision process. Reinforcement learning is based on the mathematical framework called the Markov decision process, or MDP. It is used to describe the agent and environment interactions. Markov refers to the interactive property where the future state depends on the present state. The reinforcement learning agent solves the MDP by taking a sequence of actions which leads to an optimal reward. The components for the Markov decision process are the set of observations of the different states, the set of actions the agent chooses to perform, the transition probability matrix that states the changing states in the environment, the reward model that rewards the value that the agent receives from the environments, the action performed by the agent, and also the discount factor, which is important for future rewards. The Bellman equation expresses the relationship between the value of a state and the values of its successor states. The Bellman equation averages over all the possibilities, weighting each by its probability of occurring. It states that the value of the start state must equal the discounted value of the expected next state, plus the reward expected along the way. The value function is a unique solution to the Bellman equation. The Bellman equation forms the basis of a number of ways to compute and approximate and learn the value function. Dynamic programming breaks a problem into two problems, and it utilizes the bootstrap method. It depends on the perfect model of the environment, and the two most popular methods are policy iteration and value iteration. Basically, evaluation refers to the iteration of the value function of the iterative policy. And then policy improvement depends on the computation of an improved policy given the value iteration of that policy. Taking these two computations together, you can get policy iteration and value iteration together, which are the two more important methods of dynamic programming. So either of them can be used to viably compute optimal policies and value functions for finite MDPs given a complete prior knowledge of the MDPs. Classical dynamic programming methods operate in sweeps through the state set, performing an expected update operation on each state. Each operation updates the value of one state based on the values of all possible successor states and their probabilities of occurring. Expected updates are closely related to Bellman equations. Bellman equations are basically these equations turned into assignment statements. When the updates no longer result in any changes in value, convergence has occurred to values that satisfy the corresponding Bellman equation. Value functions. Basically, almost all reinforcement learning algorithms involve estimating how good it is for the agent to be in a given state, or how good it is to perform a given action in a given state. The rewards the agent can expect to receive in the future depend on what action the agent chooses to take at that particular timestamp, and accordingly, the value functions are defined with respect to the following specific policies. Basically, the value function provides information about the quality of the state to find the optimal policy. The state value function calculates the sum of all possible actions multiplied by the probability, and the action value function is based on the policy of state action pairs. It calculates the reward for a specific action at a timestamp in state, and the agent policy is what the agent uses to know what action to perform next. Overall, the value iteration algorithm improves the estimate of Q for a state action pair in V until converted to an optimal value. The policy is a stochastic action of rules in which the agent selects actions as a function of the state. The agent's objective is to maximize the state of rewards received over time. So the optimal value is assigned to each state or the state action pair. The value function assigns the largest expected return achievable by any policy. So policy value functions are optimal and are considered the optimal policy. There are many different optimal policies for an MDP. Policy evaluation pseudocode. Here you can see the policy evaluation in the pseudocode. If you look at this, given a policy and its value function, you can quickly evaluate a change in policy for a specific state action pair. It is a natural extension to consider changes in all states for a specific action. So at each state, the action appears to be best, according to the policy or action of that particular pair. So policy evaluation is a major concept in dynamic programming, which involves computing the state value function or an arbitrary policy. So let's look at the code. We see that it initializes an array of estimates of state value function and assigns it to b. It also initializes the change in reward value to be 0. And for each state in a set of non-terminal states, we set the value to the estimated value. We calculate a new estimated value, and we calculate the maximum error between the true and estimated value until the change is smaller than the target policy. So let's take this one step further and combine policy evaluation with policy improvement. So what is this? By doing this, we are basically looking to make a new greedy policy if necessary. Which is the best way to maximize the reward? Is it the current policy, or do we need to make a new one? Or should we mostly stick to the current, which makes it a little bit greedy? It's kind of a high-level understanding that I want you to take away from this. By making it greedy with respect to the value function of the original policy, we are cheating policy improvement. It's better to select an action once in a particular state, and after that, follow that old policy than it would be to follow that policy all the time. Basically, we can expect that a particular policy will be better to select at every time the particular state is encountered, and the new policy will impact the better one overall. The new policy will be considered the new greedy policy per se, given that the argmax you see denotes the value of the expression that value maximizes. So the greedy policy takes the action that looks good for the short term, and after doing one step look ahead, according to the current policy. It is then determined if the policy is better than the current greedy policy we have right now. If it is equal to the current policy we have right now, that is not considered a better policy. Policy improvement should always be a policy with a higher return than the original policy. Basically, when you combine the policy iteration and the policy evaluation, you get value iteration. One sweep of policy evaluation is done in one sweep of improvement. You should also note that the value iteration update is basically the value evaluation update, except it requires the maximum to be taken over all actions. And also, of all actions, value iteration is achieved by turning the Bellman optimality equation into an update rule. In this video, you've learned about the Markov decision process, dynamic programming, the value function, the policy function, the Bellman equation, and how it equates to finding the value function and in turn, improved upon policies for the agent to follow.